All right, class. Today, we're taking a grand tour of the single most powerful tool in all of chemistry. Now, I know it might look like just a random chart of boxes, but I promise you, by the end of our little tour, you'll see it for what it really is, a treasure map to the elements. So, let's dive right in. I mean, seriously, what if you had a cheat sheet for all of chemistry? A guy that could predict how any substance would behave, what it would look like, how it would react, just by knowing its address. Well, that's exactly what the periodic table is. This isn't about memorizing a bunch of stuff. It's about learning to read the map. Now, this quote right here, this describes the master rule of our map, the periodic law. Yeah, it sounds super formal, I get it, but the idea behind it is actually incredibly simple and powerful. It's like the secret code that unlocks the entire table. So here's the bottom line. An element's address, its specific spot on the table, tells you its whole story. It tells you its personality. Are you dealing with something that's going to go boom? Something that won't react with anything at all? Something shiny? You just find its location and you'll know. Okay, so let's start our tour with a bird's eye view, right? The whole table is basically divided into 3 main zones. You can think of these as the continents on our map. You've got the metals, the nonmetals, and then this little strip of metalloids kind of wedged in between. Most elements fall into one of 2 camps. You're either a metal or a nonmetal, and they are pretty much total opposites. Metals, which you'll see take up most of the left side of the table, they're shiny, you can bend them, they're great conductors of electricity, and, this is key, they love to lose electrons. Nonmetals, over on the right, are their polar opposites. Dull, brittle, terrible conductors, and they are desperate to gain electrons. And then you've got this small, kind of quirky group, the metalloids. These guys literally live on the zigzaggy border between the metals and nonmetals, and they act like it. They've really got a foot in both worlds. Physically, they often look like metals, but chemically they behave a lot more like nonmetals. They're the true hybrids of our map. All right, so we've seen the continents. Now let's zoom in a bit. If the whole table is a map, then the vertical columns, or groups, are the neighborhoods. And we call them families for a really good reason. Just like a real family, all the elements living in the same column share similar traits and behaviors. But what is it that gives these families their shared personality? Well, it all boils down to one thing: valence electrons. These are the electrons in the outermost shell of an atom. You gotta get this. They are the frontline soldiers in every single chemical reaction. The number of valence electrons an element has determines literally everything about its chemical identity. So, what's the ultimate goal for every atom? It's to be stable, right? And in the world of chemistry, stability means having a full outer shell of electrons. We call this the octet rule. Think of it like the ultimate status symbol for an atom. Almost every single atom on this table is trying to get, lose, or share electrons to end up with that full set of 8, just like the super stable, cool kid noble gases. So let's meet our first family, the alkali metals, over there in group 1. Their entire identity is defined by the number 1. They have just one lonely valence electron. And you know, having just one electron is like holding a hot potato. They are absolutely desperate to get rid of it so they can become stable. And that single annoying electron defines their whole personality. Because they're so eager to just dump it on someone else, they are incredibly reactive. This is why they're these soft, shiny metals that can literally explode when they touch water. They just give up that one electron, get a positive 1 charge, and poof, they're stable and happy. Okay, now let's jump all the way across the table to group 17 and meet the halogens. Their magic number is 7. They have 7 valence electrons, which means they are so close. They're just one single electron away from that perfect stable octet. So if the alkali metals are desperate givers, the halogens are the aggressive takers. They are super reactive nonmetals because they will do almost anything to grab that one extra electron and complete their set. You can think of them as the bullies of the playground, always looking to steal an electron from someone weaker. And finally, let's meet the family that everyone else wants to be like, the noble gases in group 18. Their number? It's a perfect 8. They've already won the game. They have a full outer shell of 8 valence electrons. They've achieved the octet. Game over. And because they're already perfectly stable, they are kind of the snobs of the periodic table. They have absolutely no need to react with anyone else. They don't need to gain electrons, they don't need to lose them, they don't need to share. They are just stable, unreactive, and perfectly content all on their own. Okay, so we know the zones and we've met a few families. Now for the really, really cool part, the hidden patterns, or what we call trends. These are the predictable rules, the traffic laws of our map, if you will, that tell us how properties change as you move across a row or down a column. But before we dive into the trends, you have to understand the force behind all of them: effective nuclear charge. I know, it's a fancy term, but all it really means is the gripping power of the nucleus. The more protons you have in the nucleus, the stronger it pulls on those outer electrons. If you get this one concept, almost everything that follows is going to make perfect sense. Our first trend is a simple one: size. You know, how big is an atom? We call this its atomic radius. It's really just the distance from the center of the nucleus all the way out to that farthest valence electron. So how does size change? Well, as you move across a row from left to right, atoms actually get smaller. I know, it sounds weird, right? But think about it. You're adding more protons to the nucleus, which increases that nuclear grip and pulls all the electrons in a little tighter. But as you move down a column, atoms get way bigger, simply because you're adding whole new shells or energy levels of electrons. Next up, ionization energy. You can basically think of this as a measure of an atom's grip strength. How much energy does it take to physically rip an electron away from it? If an atom holds on to its electrons really, really tightly, we say it has a high ionization energy. And hey, are you noticing a pattern here? This trend is the complete opposite of atomic size. As you go across a row, the atoms get smaller and their grip gets tighter, so the ionization energy goes up. As you go down a column, the atoms get bigger, that outer electron is miles away from the nucleus, and it's way easier to steal, so ionization energy goes down. See, it makes perfect sense. Okay, our last big trend is electronegativity. Now, this is a little different from ionization energy. Ionization energy is about ripping an electron off a lonely, isolated atom. Electronegativity is all about an atom's ability to attract electrons from another atom when they're bonded together. It's really the measure of who wins the electron tug-of-war in a chemical bond. And no surprise here, this trend follows the exact same pattern as ionization energy. It increases as you go across the table and decreases as you go down. This makes elements up in the top right corner, like fluorine, the undisputed champions of electronegativity. I mean, fluorine is so aggressive it can even bully a noble gas into reacting. Meanwhile, the elements down in the bottom left, like francium, they barely even put up a fight. All right, so you might be thinking you've got this all figured out. Smaller atoms with a high ionization energy must be the most reactive, right? Well, not quite. When it comes to reactivity, which is arguably the most important trend of all, there is a really fascinating twist in the story. So here's the twist. Metals and nonmetals have opposite reactivity trends. For metals, whose whole game is to lose electrons, reactivity actually increases as you go down a group. Why? Because it's way easier to lose an electron from a bigger atom where it's far from the nucleus. That's why francium is the most reactive metal on the planet. But for nonmetals, which want to gain electrons, reactivity increases as you go up the group, where that nucleus has the tightest grip, and that's why fluorine is our most reactive nonmetal. So there you have it. We've covered the continents, we've met the families, and we've learned the rules of the road. We've seen how everything on this incredible map is connected in a beautiful, logical system. And here's the biggest takeaway I want you to leave with today. The periodic table is not just some poster you hang on the wall. It is your chemist's compass. It's a powerful, predictive tool that lets you understand the personality and the behavior of any element in the universe, just by knowing where it lives. So I'll leave you with this question to ponder. You now have the skills to read this secret map. You can actually predict how an element is going to behave. So, which element's personality are you most curious to explore next? What secrets are you going to uncover?